The Origin of the Universe, and Laws of Physics written by artificial intelligence ChatGPT. The Big Bang Theory. The Big Bang Theory is the most widely accepted theory for the origin of the universe. It proposes that the universe began as a singularity, an infinitely dense and hot point in space and time. Approximately 13.8 billion years ago, this singularity underwent a massive expansion, known as the Big Bang, which led to the formation of the universe as we know it today. The Big Bang Theory was first proposed in the 1920s by Belgian priest and astronomer Georges Lemaitre, based on observations of the expanding universe made by American astronomer Edwin Hubble. Hubble's observations showed that the light from distant galaxies was shifted to longer wavelengths, a phenomenon known as redshift. This indicated that the galaxies were moving away from us and that the universe was expanding. Lemaitre proposed that the universe was expanding from a single point in the past, and that this expansion was the result of a massive explosion, or the Big Bang. The theory was initially met with skepticism, but over time it has gained widespread support due to the abundance of evidence in its favor. One piece of evidence for the Big Bang Theory is the cosmic microwave background radiation, CMB, which is a faint glow of radiation that permeates the universe. The CMB was discovered in the 1960s by American radio astronomers Arno Penzias and Robert Wilson, who were attempting to study radio waves coming from the Milky Way. They found that their instruments were picking up a uniform, low-level noise that was present regardless of which direction they pointed their antenna. Further investigation revealed that this noise was actually a faint glow of microwave radiation coming from all directions in the sky. The observed temperature and spectrum of the CMB are consistent with predictions made by the Big Bang Theory, which states that the early universe was extremely hot and dense and that the CMB is the remnants of this heat and energy. Other evidence for the Big Bang Theory includes the observed abundance of light elements such as hydrogen and helium in the universe. The Big Bang Theory predicts that these elements should have been produced in the early universe during the process of nucleosynthesis, and their observed abundance is consistent with this prediction. In addition, the observed expansion of the universe is consistent with the Big Bang Theory. By studying the distance and redshift of distant galaxies, astronomers have been able to measure the expansion of the universe over time and have found that it is consistent with the predictions of the Big Bang Theory. Finally, the observed large-scale structure of the universe, including the distribution of galaxies and the large-scale patterns in their distribution, is consistent with the Big Bang Theory. The theory predicts that small density fluctuations in the early universe would have grown over time through the process of gravitational collapse, leading to the formation of the structure that we see today. The early universe. After the initial expansion of the universe during the Big Bang, the universe cooled down and became more stable. During this early phase of its existence, the universe was filled with a hot, dense plasma of particles and radiation. This plasma was composed of protons, neutrons, and electrons, as well as light particles such as photons and neutrinos. The high temperature and density of the early universe made it a chaotic and tumultuous place, with particles colliding and interacting at a furious pace. However, as the universe expanded and cooled, these particles began to slow down and come together, forming the first atoms. This process, known as recombination, occurred when the universe was approximately 380,000 years old. At this point, the temperature of the universe had dropped to the point where protons and electrons could join together to form hydrogen atoms. These atoms were able to capture and hold on to the photons that had been flying freely through the plasma, and the universe became transparent to light. The photons that were released during recombination have been traveling through the universe ever since, and they make up the cosmic microwave background radiation, CMB, that we observe today. The CMB provides us with a baby picture of the universe, allowing us to see what the universe looked like in its infancy. The early universe was also marked by a period of rapid expansion known as cosmic inflation. This period of inflation is thought to have occurred between 10⁻36 and 10⁻32 seconds after the Big Bang. During inflation, the universe expanded much faster than the speed of light, leading to the smooth and uniform distribution of matter that we see today. The theory of cosmic inflation was first proposed in the 1980s by American physicist Alan Guth, and it has been supported by a variety of observations. These include the observed flatness of the universe, the observed uniformity of the CMB, and the observed scale invariant fluctuations in the CMB. The concept of cosmic inflation is a revolutionary one, as it suggests that the universe underwent a period of rapid expansion in its earliest moments. This expansion would have smoothed out any irregularities in the distribution of matter, explaining why the universe appears so uniform on a large scale. Inflation also provides a possible explanation for the observed large-scale structure of the universe, as small density fluctuations in the early universe could have been amplified by the expansion during inflation. The formation of galaxies and structure in the universe. After the early universe had cooled and become transparent to light, it was filled with a diffuse gas of hydrogen and helium. Over time, this gas began to clump together due to the force of gravity, forming the first stars and galaxies. The process of galaxy formation is a complex one, and it is still not fully understood by scientists. However, it is thought to involve the collapse of large clouds of gas and dust under their own gravity. As these clouds collapse, they begin to spin, forming a disk-like structure. At the center of the disk, the gas and dust become denser and hotter, eventually forming a massive, luminous object known as a quasar. Quasars are some of the most powerful objects in the universe, and they are thought to be powered by supermassive black holes at their centers. As the quasar radiates energy, it blows out much of the surrounding gas and dust, halting the process of star formation. This process is thought to be responsible for the observed downsizing of galaxies, in which smaller galaxies tend to form more stars than larger ones. The formation of galaxies and the large-scale structure of the universe are also thought to be influenced by dark matter, a mysterious and elusive substance that makes up approximately 85% of the mass of the universe. Dark matter does not interact with light or other forms of electromagnetic radiation, making it invisible to telescopes and other instruments. However, its presence can be inferred through its gravitational effects on visible matter. Dark matter is thought to play a crucial role in the formation of galaxies and the large-scale structure of the universe. It is believed to act as a scaffolding, providing the gravitational glue that holds galaxies and clusters of galaxies together. Without dark matter, it is thought that the universe would be a much less organized place, with fewer and less well-defined structures. Quasars. Quasars, also known as quasistellar radio sources, QSOs, are some of the most luminous and energetic objects in the universe. They are thought to be powered by supermassive black holes at the centers of galaxies, and they are capable of emitting vast amounts of energy in the form of electromagnetic radiation. Quasars are extremely distant objects, with many of them located at the edge of the observable universe. They are therefore extremely difficult to study, and much about them is still not fully understood. The first quasar was discovered in 1963 by American astronomers Martin Schmidt and Alan Sandage. Schmidt was studying the spectrum of a distant, seemingly star-like object when he noticed that the lines in the spectrum were shifted to longer wavelengths, indicating that the object was moving away from us at a high speed. This phenomenon, known as redshift, is caused by the expansion of the universe, and it is a key piece of evidence for the Big Bang theory. Based on the observed redshift, Schmidt and Sandage calculated that the quasar was located over 2 billion light-years away, making it one of the most distant objects ever observed at the time. Since the discovery of the first quasar, thousands more have been found, and they have become some of the most valuable objects for studying the early universe. Quasars are thought to be powered by supermassive black holes at their centers, which can have masses millions or billions of times greater than that of the Sun. As material falls into the black hole, it is heated to extremely high temperatures, causing it to radiate energy in the form of electromagnetic radiation. This radiation is what we observe as a quasar. Quasars are also thought to play a key role in the evolution of galaxies. As they emit vast amounts of energy, they can blow out much of the surrounding gas and dust, halting the process of star formation. This process is thought to be responsible for the observed downsizing of galaxies, in which smaller galaxies tend to form more stars than larger ones. The origin of black holes. Black holes are some of the most mysterious and intriguing objects in the universe. They are regions of space where the normal laws of physics break down, and they are defined by their intense gravitational pull, which is so strong that not even light can escape it. There are several different types of black holes, including stellar black holes, intermediate mass black holes, and supermassive black holes. Stellar black holes are the smallest and most common type, with masses ranging from a few to tens of times that of the Sun. They are thought to form when the core of a massive star collapses at the end of its life. Intermediate mass black holes are larger, with masses ranging from hundreds to tens of thousands of times that of the Sun. They are thought to be the seeds from which supermassive black holes form, and they may be the result of the merger of multiple smaller black holes. Supermassive black holes are the largest type, with masses ranging from millions to billions of times that of the Sun. They are thought to be at the center of most, if not all, galaxies, including our own Milky Way. It is believed that supermassive black holes form through the merger and accretion of smaller black holes and other dense objects, such as neutron stars. The exact process by which black holes form is not fully understood, and it is an active area of research in astrophysics. However, it is thought that the intense gravitational forces present in the early universe may have played a role in their formation. The future of the universe. The future of the universe is a topic of much speculation and debate among scientists. There are a number of different scenarios for the ultimate fate of the universe, each with its own set of supporting evidence. One possibility is that the expansion of the universe will continue indefinitely, leading to a big freeze in which the universe becomes too diffuse and cold to support the formation of new stars and galaxies. This scenario is known as the heat death of the universe. Another possibility is that the expansion of the universe will eventually slow down and stop, leading to a big crunch in which the universe collapses back in on itself. This scenario is known as the Big Crunch or Big Collapse. A third possibility is that the expansion of the universe will continue, but at a slower and slower rate, eventually reaching a state of coasting in which it expands indefinitely but at a constant rate. This scenario is known as the Big Coast. Which of these scenarios will ultimately come to pass is not yet known, and it may be that the future of the universe is something completely different from any of these scenarios. Much more research is needed to better understand the long-term evolution of the universe. The heat death of the universe. The heat death of the universe is a scenario in which the expansion of the universe will continue indefinitely, leading to a state of maximum entropy in which the universe becomes too diffuse and cold to support the formation of new stars and galaxies. This scenario is based on the idea that the total energy of the universe is finite, and as the universe expands, this energy is spread out over an increasingly large volume. According to the second law of thermodynamics, the total entropy, or disorder, of a closed system will always increase over time. In the case of the universe, this increase in entropy would eventually lead to a state of thermal equilibrium, in which the temperature of the universe becomes uniform and there is no longer a source of energy to power the formation of new stars and galaxies. This scenario is often referred to as the heat death of the universe, as it represents the ultimate demise of the universe as we know it. However, it should be noted that the heat death of the universe is a very long way off, as it is estimated to occur on a timescale of trillions of years. In fact, the current age of the universe is only around 14 billion years, a tiny fraction of the time it would take for the heat death to occur. The heat death of the universe is just one possible scenario for the ultimate fate of the universe, and it is based on certain assumptions about the nature of the universe, such as the existence of dark energy and the total amount of energy it contains. Other scenarios, such as the Big Crunch and the Big Coast, also exist and are worth considering. The Big Crunch. The Big Crunch, also known as the Big Collapse, is a scenario in which the expansion of the universe will eventually slow down and stop, leading to a reversal of the Big Bang and the collapse of the universe back in on itself. This scenario is based on the idea that the total mass of the universe is sufficient to overcome the expansion caused by the Big Bang, eventually leading to a collapse. The idea of the Big Crunch dates back to the 1930s, when Russian cosmologist Georgy Gamow proposed that the expansion of the universe would eventually slow down and stop, leading to a contraction. However, the idea fell out of favor in the 1970s with the discovery of dark energy, which is thought to be driving the acceleration of the expansion of the universe. Dark energy is a mysterious and elusive substance that is thought to make up approximately 73% of the mass energy budget of the universe. It is characterized by its negative pressure, which acts to drive the expansion of the universe. The discovery of dark energy has led many scientists to believe that the expansion of the universe will continue indefinitely, leading to a heat death scenario. However, it is still possible that the Big Crunch could occur if the amount of dark energy in the universe Despite the presence of dark energy, it is still possible that the Big Crunch could occur if the amount of dark energy in the universe decreases over time. This could happen if the dark energy decays into other forms of matter or energy, leading to a decrease in its negative pressure and a slowing of the expansion of the universe. If the expansion of the universe does slow down and stop, it is likely that it will do so gradually, over a period of billions of years. During this time, the universe would continue to expand, but at a slower and slower rate. Eventually, the expansion would come to a halt, and the universe would begin to contract. As the universe contracts, the density and temperature of the universe would increase, leading to the formation of new stars and galaxies. This process would continue until the universe reaches a state of maximum density and temperature, at which point the contraction would stop and the universe would enter a state of equilibrium. The exact nature of the Big Crunch is not well understood, and it is likely that it would be a complex and chaotic process. Some scientists have even suggested that the Big Crunch could lead to the formation of a new universe, potentially giving rise to a cycle of expansion and contraction that has been ongoing for eternity. The Big Crunch is just one possible scenario for the ultimate fate of the universe, and it is based on certain assumptions about the nature of the universe, such as the amount of matter and energy it contains and the properties of dark energy. While the Big Crunch is a fascinating possibility, it is not currently supported by observations, and it is possible that the universe will follow a different path entirely. Other scenarios, such as the heat death and the Big Coast, also exist and are worth considering. Here is Chapter 10. The Big Coast. The Big Coast is a scenario in which the expansion of the universe will continue, but at a slower and slower rate, eventually reaching a state of coasting in which it expands indefinitely but at a constant rate. This scenario is based on the idea that the total mass and energy of the universe are balanced in such a way that the expansion will slow down but never completely stop. The Big Coast scenario is similar to the heat death of the universe, in that it involves the expansion of the universe continuing indefinitely. However, it differs in that the expansion of the universe does not slow down to the point where the formation of new stars and galaxies is no longer possible. Instead, the expansion would reach a state of equilibrium, with the universe continuing to expand at a constant rate forever. The Big Coast scenario is based on the idea that the total mass and energy of the universe are balanced in such a way that the expansion will slow down but never completely stop. This balance would be achieved through the presence of dark energy, a mysterious and elusive substance that is thought to make up approximately 73% of the mass energy budget of the universe. Dark energy is characterized by its negative pressure, which acts to drive the expansion of the universe. If the amount of dark energy in the universe is sufficient to overcome the gravitational forces that tend to slow the expansion could continue indefinitely, leading to a Big Coast scenario. The Big Coast is just one possible scenario for the ultimate fate of the universe, and it is based on certain assumptions about the nature of the universe, such as the amount of matter and energy it contains and the properties of dark energy. While the Big Coast is a fascinating possibility, it is not currently supported by observations, and it is possible that the universe will follow a different path entirely. Other scenarios, such as the heat death and the Big Crunch, also exist and are worth considering. Much more research is needed to better understand the long-term evolution of the universe and to determine which of these scenarios, if any, is most likely. Dark matter. Dark matter is a mysterious and elusive substance that is thought to make up approximately 27% of the mass energy budget of the universe. Despite its name, dark matter does not emit, absorb, or reflect light, which makes it invisible to telescopes and other instruments that rely on electromagnetic radiation to detect objects in the universe. The existence of dark matter was first proposed in the 1930s by Swiss astronomer Fritz Zwicky, who noticed that the mass of galaxies and galaxy clusters appeared to be much greater than could be accounted for by the visible matter they contained. Zwicky proposed that the extra mass was made up of an unseen substance, which he dubbed dark matter. Since Zwicky's pioneering work, a wealth of evidence has accumulated in support of the existence of dark matter. This evidence includes the observed rotational curves of galaxies, the gravitational lensing of light by galaxy clusters, and the distribution of matter in the universe. Despite this evidence, the nature of dark matter remains a mystery. It is not known what dark matter is made of, and it is possible that it is composed of particles that have yet to be discovered. There are several leading candidates for the makeup of dark matter, including weakly interacting massive particles, WIMPs, and axions, but none have yet been conclusively detected. The search for dark matter is an active area of research in astrophysics, and it is hoped that future observations and experiments will shed more light on this mysterious substance. One of the main challenges in studying dark matter is that it does not interact with light or other forms of electromagnetic radiation, which makes it difficult to detect directly. Instead, the presence of dark matter is inferred through its gravitational effects on visible matter. Despite the challenges in studying dark matter, it is clear that it plays a vital role in the structure and evolution of the universe. It is thought to be the dominant form of matter in the universe, and it is responsible for holding galaxies and galaxy clusters together through its gravitational pull. Without dark matter, the universe as we know it would not exist. It is an essential component of the cosmic web of matter and energy that shapes the universe on the largest scales. The search for dark matter is ongoing, and it is hoped that future observations and experiments will provide more insight into this mysterious substance and its role in the universe. Chapter 12: The Search for Dark Matter. The search for dark matter is an active and ongoing area of research in astrophysics. Despite its importance in shaping the structure and evolution of the universe, the nature of dark matter remains a mystery. It is not known what dark matter is made of, and it is possible that it is composed of particles that have yet to be discovered. One of the main challenges in studying dark matter is that it does not interact with light or other forms of electromagnetic radiation, which makes it difficult to detect directly. Instead, the presence of dark matter is inferred through its gravitational effects on visible matter. There are several leading candidates for the makeup of dark matter, including weakly interacting massive particles, WIMPs, and axions, but none have yet been conclusively detected. The search for these particles is being pursued through a variety of means, including underground detectors, particle accelerators, and telescopes. One of the main techniques used in the search for dark matter is indirect detection, in which the products of dark matter annihilations or decays are sought. This involves searching for high-energy particles, such as gamma rays and cosmic rays, that are thought to be produced when dark matter particles collide or decay. Another technique used in the search for dark matter is direct detection, in which the interactions of dark matter particles with normal matter are sought. This involves using detectors to search for the tiny amounts of energy that are transferred when dark matter particles pass through the detector. The search for dark matter is a complex and challenging endeavor, and it is likely to continue for many years to come. It is hoped that the next decade will bring major breakthroughs in our understanding of this mysterious substance and its role in the universe. Despite the challenges in studying dark matter, it is clear that it plays a vital role in the structure and evolution of the universe. It is thought to be the dominant form of matter in the universe, and it is responsible for holding galaxies and galaxy clusters together through its gravitational pull. The search for dark matter is a vital part of understanding the universe and our place within it. It is an exciting and dynamic field of research, and it has the potential to revolutionize our understanding of the universe and its workings. Chapter 13: The Inflationary Universe. The inflationary universe is a theory that proposes that the universe underwent a rapid expansion during its early stages, a fraction of a second after the Big Bang. This rapid expansion, known as cosmic inflation, is thought to have smoothed out the universe and laid the foundations for the large-scale structure we see today. The idea of cosmic inflation was first proposed by American physicist Alan Guth in 1979, and it has since gained widespread support from the scientific community. The theory of cosmic inflation is based on the idea that the universe underwent a phase of exponential expansion during its early stages, driven by a mysterious and elusive substance known as the inflaton field. The inflaton field is thought to have been present in the universe during the first fraction of a second after the Big Bang, and it is believed to have triggered the rapid expansion of the universe. As the universe expanded, the inflaton field decayed, releasing its energy and ending the phase of cosmic inflation. The theory of cosmic inflation is supported by a wealth of evidence, including observations of the cosmic microwave background radiation and the large-scale structure of the universe. It is an elegant and powerful theory that provides a compelling explanation for the observed features of the universe. Chapter 14: The Multiverse Hypothesis. The multiverse hypothesis is a theory that proposes the existence of multiple universes, beyond our own observable universe. These universes, or parallel universes, are thought to be separate and distinct from our own, and they may have different physical laws, constants, and even histories. The idea of the multiverse has been around for centuries, and it has gained renewed attention in recent years due to advances in theoretical physics and cosmology. There are several different versions of the multiverse hypothesis, including the idea of a many-worlds interpretation of quantum mechanics, eternal inflation, and brane cosmology. One of the main motivations for the multiverse hypothesis is the problem of the fine-tuning of the universe. This refers to the observation that the physical constants and laws of the universe appear to be finely tuned to allow for the existence of life, leading some to speculate that there must be multiple universes with different sets of physical laws in order to explain the observed fine-tuning. While the existence of the multiverse is still purely theoretical and has not yet been directly observed, it is an interesting and provocative idea that has garnered significant attention from the scientific community. It is possible that the multiverse may one day be directly detected through observations of the cosmic microwave background radiation or other means, but much more research is needed to determine its validity. Chapter 15, The String Theory, including a deep overview of the origin of the theory. The string theory is a theoretical framework that aims to reconcile quantum mechanics and general relativity, two of the pillars of modern physics. It proposes that the fundamental building blocks of the universe are not point-like particles, as previously thought, but rather one-dimensional strings that vibrate at different frequencies. The origins of the string theory can be traced back to the late 1960s and early 1970s, when physicists were attempting to understand the fundamental nature of the strong nuclear force, the force that holds protons and neutrons together in the nucleus of an atom. It was discovered that the mathematical equations used to describe the strong nuclear force were very similar to those used to describe the vibrational modes of strings, leading some physicists to speculate that the strong nuclear force might be mediated by strings. The string theory was further developed in the 1980s and 1990s, when it was realized that it could potentially provide a unified theory of all physical phenomena, including gravity. The string theory is based on the idea that the universe has more than 3 dimensions of space and 1 dimension of time, and that these extra dimensions are compactified or hidden from our everyday experience. This additional complexity allows for the existence of different types of strings and the possibility of different vibrational modes, leading to a rich and varied spectrum of particles and forces. One of the key features of the string theory is its ability to incorporate the concept of duality, in which seemingly different physical phenomena are actually different manifestations of the same underlying principles. This includes the duality between particles and waves, and the duality between the strong and weak nuclear forces. While the string theory is an elegant and promising framework for understanding the fundamental nature of the universe, it is still a work in progress and much more research is needed to fully understand its implications. The string theory is a work in progress, and much more research is needed to fully understand its implications and determine its validity. Despite its potential, the string theory remains highly speculative and is not yet supported by empirical evidence. It is possible that the string theory may one day provide a complete and unified description of all physical phenomena, but much more work is needed to confirm this. Chapter 16, The Holographic Principle. The holographic principle is a theoretical concept that proposes that the information content of a region of space can be described by a boundary surrounding that region, rather than by the volume within that region. This concept, which is inspired by the mathematical structure of black hole entropy, has implications for the nature of space, time, and the fundamental laws of physics. One of the main motivations for the holographic principle is the problem of the black hole information paradox, which arises when trying to reconcile the laws of quantum mechanics with the laws of general relativity. The paradox arises because the laws of general relativity predict that information that falls into a black hole is lost forever, while the laws of quantum mechanics dictate that information cannot be destroyed. The holographic principle offers a possible resolution to the black hole information paradox by suggesting that the information contained within a region of space is actually encoded in the surface area of the boundary surrounding that region. This implies that the three-dimensional world we experience is actually a projection of information stored on a two-dimensional surface, much like a hologram. While the holographic principle is an intriguing and provocative idea, it is still a work in progress and much more research is needed to fully understand its implications and determine its validity. It is possible that the holographic principle may one day provide a deeper understanding of the nature of space and time, but much more work is needed to confirm this. Chapter 17, The Cosmic Landscape. The cosmic landscape is a theoretical concept that proposes the existence of a vast landscape of possible universes, each with its own set of physical laws and constants. This concept is based on the idea of string theory and the multiverse hypothesis, and it suggests that our observable universe is just one possible configuration within a much larger and more diverse set of possible universes. The cosmic landscape is based on the idea that the fundamental constants and laws of physics, such as the strength of the strong nuclear force and the mass of the electron, may vary from one universe to another. This variation is thought to be due to the different ways in which the extra dimensions of the universe can be compactified or hidden from our everyday experience. The cosmic landscape is an interesting and provocative idea that has garnered significant attention from the scientific community. It is thought to provide a possible explanation for the observed fine-tuning of the universe, and it may also have implications for the likelihood of life and intelligent beings evolving in different parts of the landscape. While the cosmic landscape is still purely theoretical and has not yet been directly observed, it is an interesting and provocative idea that has the potential to revolutionize our understanding of the universe and our place within it. It is possible that the cosmic landscape may one day be directly detected through observations of the cosmic microwave background radiation or other means, but much more research is needed to determine its validity. Chapter 18, The Anthropic Principle. The anthropic principle is a theoretical concept that suggests that the observed properties of the universe must be compatible with the existence of intelligent life, because if they were not, we would not be here to observe them. This principle has been used to explain the apparent fine-tuning of the universe, and it has implications for our understanding of the universe and our place within it. There are several different versions of the anthropic principle, including the weak anthropic principle, the strong anthropic principle, and the final anthropic principle. The weak anthropic principle states that the observed properties of the universe must be compatible with the existence of life, but does not necessarily require the existence of intelligent life. The strong anthropic principle goes further, suggesting that the universe must be conducive to the existence of intelligent life, and that our observable universe is only one possible configuration within a much larger set of possible universes. The final anthropic principle suggests that the universe must be conducive to the existence of observers, and that the ultimate purpose of the universe is the emergence of self-aware beings. The anthropic principle is a controversial and highly speculative idea that has garnered significant attention from the scientific community. While it is an interesting and provocative concept, it is still a work in progress and much more research is needed to fully understand its implications and determine its validity. It is possible that the anthropic principle may one day provide a deeper understanding of the role of intelligent life in the universe, but much more work is needed to confirm this. Chapter 19, The Cyclic Universe. The cyclic universe is a theoretical concept that proposes that the universe goes through cycles of expansion and contraction, or bangs and crunches. This concept is based on the idea of eternal inflation and the multiverse hypothesis, and it suggests that our observable universe is just one phase in an infinite cycle of cosmic evolution. The cyclic universe is based on the idea that the universe is not a one-time event, but rather a continually repeating process. This process is thought to be driven by the expansion and contraction of the extra dimensions of the universe, which are compactified or hidden from our everyday experience. Each cycle is thought to be preceded by a Big Bang and followed by a big crunch in which the universe collapses back in on itself. The cyclic universe is an interesting and provocative idea that has garnered significant attention from the scientific community. It is thought to provide a possible explanation for the observed fine-tuning of the universe, and it may also have implications for the ultimate fate of the universe and the nature of time. While the cyclic universe is still purely theoretical and has not yet been directly observed, it is an interesting and provocative idea that has the potential to revolutionize our understanding of the universe and its evolution. It is possible that the cyclic universe may one day be directly detected through observations of the cosmic microwave background radiation or other means, but much more research is needed to determine its validity. Chapter 20, The simulation hypothesis. The simulation hypothesis is a theoretical concept that proposes that our reality is actually a simulated or virtual reality, created by a superintelligent being or civilization. This concept, which has gained significant attention in recent years, is based on the idea that advanced civilizations may have the ability to create highly realistic simulations of reality, and that it is possible that we are living in such a simulation. The simulation hypothesis is motivated by the observation that the laws of physics and the structure of the universe appear to be highly regular and systematic, leading some to speculate that they may be the product of a conscious or unintentional design. It is also motivated by the idea that advanced civilizations may have the ability to create highly realistic simulations of reality, and that it is possible that we are living in such a simulation. The simulation hypothesis is a highly speculative and controversial idea, and it has not yet been proven or directly observed. It is an interesting and provocative concept that has the potential to revolutionize our understanding of the nature of reality, but much more research is needed to determine its validity. Chapter 21, The Quantum Multiverse. The quantum multiverse, also known as the many-worlds interpretation of quantum mechanics, is a theoretical concept that proposes the existence of an infinite number of parallel universes, each corresponding to a different outcome of a quantum event. This concept is based on the principles of quantum mechanics, and it suggests that our observable universe is just one possible outcome of an infinite number of possible outcomes. The quantum multiverse is based on the idea that the principles of quantum mechanics, which govern the behavior of subatomic particles, allow for multiple outcomes of a quantum event to simultaneously exist in separate parallel universes. This means that for every quantum event that occurs, there is a corresponding universe in which each possible outcome occurs. The quantum multiverse is an interesting and provocative idea that has garnered significant attention from the scientific community. It is thought to provide a possible explanation for the observed wave-particle duality of quantum particles, and it may also have implications for the ultimate nature of reality and the role of consciousness. While the quantum multiverse is still purely theoretical and has not yet been directly observed, it is an interesting and provocative idea that has the potential to revolutionize our understanding of the universe and its underlying structure. It is possible that the quantum multiverse may one day be directly detected through observations of quantum phenomena or other means, but much more research is needed to determine its validity. Chapter 22, The Big Freeze, an overview. The Big Freeze, also known as the heat death of the universe, is a theoretical end state of the universe in which the universe becomes too diffuse and dilute to sustain the formation of new stars and galaxies, and all matter and energy eventually dissipates into a uniform state of energy. This end state is predicted by the second law of thermodynamics, which states that entropy, or the measure of disorder in a system, always increases over time. The concept of the Big Freeze dates back to the 19th century, when scientists first began to understand the principles of thermodynamics and their implications for the ultimate fate of the universe. In the early 20th century, physicists such as Sir Arthur Eddington and Hermann Bondi proposed the idea of the heat death of the universe as a possible end state, based on the second law of thermodynamics and the observed expansion of the universe. The Big Freeze is thought to be the ultimate fate of the universe, unless something intervenes to halt or reverse the increasing entropy. It is predicted to occur after the current expansion of the universe comes to an end and the universe begins to contract, eventually leading to a big crunch in which the universe collapses back in on itself. After the Big Crunch, the universe is thought to re-expand in a new cycle of cosmic evolution, leading to a possible scenario known as the Big Bounce. The Big Freeze is a fascinating and thought-provoking concept that has garnered significant attention from the scientific community. While it is still purely theoretical and has not yet been directly observed, it is an interesting and provocative idea that has the potential to revolutionize our understanding of the ultimate fate of the universe. Chapter 23, The Holographic Universe, an overview. The holographic universe is a theoretical concept that proposes that the universe is a holographic projection, much like a 3D movie, and that the observed laws of physics and the structure of the universe are the result of information stored on a cosmic holographic boundary. This concept is based on the principles of quantum mechanics and the holographic principle, and it suggests that our observable universe is just one aspect of a much larger and more fundamental reality. The origins of the holographic universe can be traced back to the early 20th century, when physicists such as Max Planck and Albert Einstein began to explore the fundamental nature of reality and the role of information in the universe. In the late 20th century, physicists such as Gerard T. Hooft and Leonard Susskind developed the holographic principle, which proposes that the information contained in a region of space is equivalent to the information encoded on the surface bounding that region. This principle led to the development of the holographic universe as a theoretical concept. The holographic universe is based on the idea that the fundamental building blocks of reality are not physical objects, but rather bits of information. This information is thought to be encoded on a cosmic holographic boundary, which is a surface or boundary that surrounds the universe and contains all the information needed to describe the universe. The observed laws of physics and the structure of the universe are thought to be the result of this encoded information being projected or unfolded into the three-dimensional space we experience. The holographic universe is an interesting and provocative idea that has garnered significant attention from the scientific community. It is thought to provide a possible explanation for the observed holographic duality of quantum particles, and it may also have implications for the ultimate nature of reality and the role of consciousness. While the holographic universe is still purely theoretical and has not yet been directly observed, it is an interesting and provocative idea that has the potential to revolutionize our understanding of the universe and its underlying structure. It is possible that the holographic universe may one day be directly detected through observations of quantum phenomena or other means, but much more research is needed to determine its validity. Chapter 24, The String Theory Landscape, an Overview. The string theory landscape is a theoretical concept that proposes the existence of a vast landscape of possible universes, each corresponding to a different vacuum state or configuration of the fundamental building blocks of the universe. This concept is based on the principles of string theory, and it suggests that our observable universe is just one possible configuration of an infinite number of possible configurations. The origins of the string theory landscape can be traced back to the early 20th century, when physicists such as Albert Einstein and Paul Dirac developed the concept of fundamental particles as the building blocks of the universe. In the late 20th century, physicists such as John Schwartz and Michael Green developed string theory, which proposes that the fundamental building blocks of the universe are not particles, but rather one-dimensional strings that vibrate at different frequencies. These strings are thought to be able to form different configurations, or vacuum states depending on the specific arrangement and interactions of the strings. The string theory landscape is based on the idea that each of these vacuum states corresponds to a different universe, with its own set of physical laws and properties. This means that the universe we observe is just one possible configuration of an infinite number of possible configurations, each corresponding to a different vacuum state in the string theory landscape. The observed laws of physics and the structure of the universe are thought to be the result of the specific vacuum state or configuration of strings in our universe. The string theory landscape is an interesting and provocative idea that has garnered significant attention from the scientific community. It is thought to provide a possible explanation for the observed fine-tuning of the universe, and it may also have implications for the ultimate nature of reality and the role of consciousness. While the string theory landscape is still purely theoretical and has not yet been directly observed, it is an interesting and provocative idea that has the potential to revolutionize our understanding of the universe and its underlying structure. The oscillating universe theory. The oscillating universe theory is a cosmological model that suggests that the universe goes through an endless cycle of expansion and contraction, with each cycle ending in a big crunch and beginning with a Big Bang. This theory is an alternative to the widely accepted Big Bang theory, which posits that the universe began with a single, explosive event and has been expanding ever since. The oscillating universe theory was first proposed in the 1930s by the Indian physicist Satyendranath Bose and the Russian physicist Georges Lemaitre, but it did not gain widespread attention until the 1950s, when the physicist Fred Hoyle developed a variant of the theory known as the steady-state theory. Hoyle's theory was an attempt to explain the observed abundance of hydrogen and helium in the universe without invoking a Big Bang. One of the key pieces of evidence in favor of the oscillating universe theory is the cosmic microwave background radiation, which is thought to be residual radiation left over from the Big Bang. According to the oscillating universe theory, this radiation would be present in each cycle of expansion and contraction, providing a link between successive cycles. However, the oscillating universe theory has also faced significant challenges. One of the main problems is that it is difficult to reconcile the theory with the observed expansion of the universe, which appears to be accelerating rather than slowing down as it would in an oscillating universe. Additionally, there is no clear mechanism by which the universe could undergo a contraction phase, as the laws of physics as we understand them do not allow for such a process. Despite these challenges, the oscillating universe theory remains an interesting and potentially viable alternative to the Big Bang theory, and it continues to be studied by researchers today. The nature of the universe. The nature of the universe is a topic that has puzzled and fascinated humans for centuries. From the earliest civilizations to the present day, people have sought to understand the origins and ultimate fate of the universe, as well as its size, shape, and structure. One of the most fundamental questions about the universe is its size. Modern measurements suggest that the observable universe is around 93 billion light-years in diameter, and it is estimated to contain more than 100 billion galaxies. However, it is important to note that this represents only a small portion of the universe, as the vast majority of the universe is thought to be made up of dark matter and dark energy, which are mysterious substances that do not interact with light and are therefore invisible to telescopes. Another key aspect of the universe is its structure. Observations of the distribution of galaxies and other large structures in the universe suggest that it is made up of a network of filaments and voids, with galaxies and galaxy clusters located at the intersections of the filaments. This structure is thought to be the result of cosmic inflation, a process that occurred during the early stages of the universe and caused the universe to expand at an exponential rate. Despite our growing understanding of the universe, there are still many mysteries that remain unsolved. For example, it is still not clear what the ultimate fate of the universe will be, or whether it is the only universe that exists. Some theories, such as the multiverse theory, suggest that there may be multiple universes beyond our own, each with its own set of physical laws and properties. However, these theories are still highly speculative and have not yet been proven. The laws of physics. The laws of physics are the fundamental principles that govern the behavior of the universe. These laws describe how objects move, how energy is transferred, and how matter interacts with itself and its surroundings. There are many different laws of physics, ranging from simple concepts such as the law of gravity to more complex principles such as quantum mechanics. One of the most famous laws of physics is the law of universal gravitation, which was first proposed by Sir Isaac Newton in the 17th century. This law states that every object in the universe attracts every other object with a force that is directly proportional to the masses of the objects and inversely proportional to the square of the distance between them. This law explains why objects fall to the ground and why the planets orbit the Sun. Another important law of physics is the law of conservation of energy, which states that energy cannot be created or destroyed, only transformed from one form to another. This law has many important implications, including the fact that the total amount of energy in the universe is constant. There are also many other laws of physics that describe the behavior of matter and energy under different conditions. For example, the laws of thermodynamics describe how heat is transferred and how work is done, while the laws of electromagnetism describe how electric and magnetic fields interact. Overall, the laws of physics play a crucial role in our understanding of the universe and how it works. They provide a framework for predicting the outcomes of experiments and for understanding the behavior of matter and energy on a fundamental level. The theory of relativity. One of the most important developments in the history of physics was the theory of relativity, which was proposed by Albert Einstein in the early 20th century. This theory revolutionized our understanding of space and time and has had a profound impact on many areas of science, including cosmology, astronomy, and particle physics. There are two parts to the theory of relativity: the special theory of relativity and the general theory of relativity. The special theory of relativity is based on the idea that the laws of physics are the same for all observers, regardless of their relative motion. This theory introduced the concept of space-time, which is a four-dimensional framework that combines space and time into a single entity. The general theory of relativity is an extension of the special theory of relativity that takes into account the effects of gravity. According to this theory, gravity is not a force, but rather the curvature of space-time caused by the presence of mass or energy. This theory explains the orbits of the planets and the behavior of light around massive objects, such as black holes. The theory of relativity has been confirmed by numerous experiments and observations, including the deflection of light by the Sun and the redshift of light from distant galaxies. It has also led to many groundbreaking predictions, such as the existence of black holes and the expansion of the universe. Overall, the theory of relativity is a fundamental pillar of modern physics and has had a profound impact on our understanding of the nature of the universe. Quantum mechanics. Another major development in the field of physics was the development of quantum mechanics, a theory that describes the behavior of matter and energy on a very small scale. Quantum mechanics is based on the idea that particles such as atoms and subatomic particles can exhibit both wave-like and particle-like properties, and that their behavior can be described using probability rather than definite outcomes. One of the key principles of quantum mechanics is the uncertainty principle, which states that it is impossible to know both the exact position and momentum of a subatomic particle at the same time. This principle has important implications for our understanding of the fundamental nature of the universe and has led to many counterintuitive predictions, such as the possibility of particles being in two places at the same time. Quantum mechanics has had a major impact on many areas of science, including chemistry, materials science, and electronics. It has also led to the development of technologies such as transistors, lasers, and magnetic resonance imaging, MRI. Despite its successes, quantum mechanics is still a subject of ongoing research and debate, as it challenges some of the traditional assumptions of classical physics and raises many questions about the nature of reality. However, it remains a fundamental theory that is essential for our understanding of the universe at the most fundamental level. The Standard Model of Particle Physics. The Standard Model of Particle Physics is a theory that describes the fundamental building blocks of matter and the forces that govern their behavior. The Standard Model is based on the idea that all matter is made up of particles called quarks and leptons, which are held together by force-carrying particles called gauge bosons. There are 6 types of quarks and 6 types of leptons, and they are organized into 3 generations, with each generation consisting of 2 quarks and 2 leptons. The gauge bosons include the photon, which carries the electromagnetic force, and the W and Z bosons, which carry the weak nuclear force. The Standard Model also includes the Higgs boson, a particle that was discovered at the Large Hadron Collider in 2012 and is responsible for giving other particles mass. The discovery of the Higgs boson was a major milestone in particle physics and provided strong evidence in support of the Standard Model. Despite its successes, the Standard Model is not a complete theory, as it does not include the gravitational force or explain the observed dark matter and dark energy in the universe. However, it is an essential framework for understanding the behavior of matter and energy at the most fundamental level, and it continues to be an active area of research and development. The evolution of the universe. The evolution of the universe is a vast and complex topic that encompasses the entire history of the universe, from its earliest moments to the present day. According to the Big Bang Theory, the universe began around 13.8 billion years ago in a massive explosion that marked the start of time and space as we know it. In the moments after the Big Bang, the universe was extremely hot and dense, and it expanded and cooled as it expanded. As the universe cooled, matter began to condense into clumps, eventually forming the first stars and galaxies. Over time, these stars and galaxies have evolved and changed, with some stars burning out and forming new objects such as black holes and neutron stars. The universe has also continued to expand, and it is currently thought to be expanding at an accelerating rate due to the influence of dark energy. The evolution of the universe is a complex and ongoing process, and there is still much that scientists do not understand about its history and ultimate fate. However, by studying the remnants of the early universe, such as the cosmic microwave background radiation, and by observing the structures and behaviors of galaxies and other celestial objects, scientists are working to piece together the story of the universe and to understand its past, present, and future. The search for extraterrestrial life. The search for extraterrestrial life, or the search for life beyond the Earth, is a topic that has long captivated the imagination of humans. For centuries, people have speculated about the possibility of life on other planets, and in recent decades, scientists have made significant strides in the search for extraterrestrial life. One of the key tools that scientists use in the search for extraterrestrial life is the telescope, which allows them to study the atmospheres and surfaces of other planets and look for signs of life. In recent years, telescopes such as the Kepler Space Telescope and the TRAPPIST-1 telescope have discovered thousands of exoplanets, or planets outside of our solar system, and many of these planets are located in the habitable zone of their star, where conditions might be suitable for life. In addition to looking for life on other planets, scientists are also studying the origins of life on Earth and searching for signs of life on other bodies in the solar system, such as Mars and Europa. These efforts have led to the discovery of microbial life on Earth in extreme environments, such as deep underground and in acidic hot springs, which has implications for the potential for life on other worlds. Overall, the search for extraterrestrial life is a complex and multifaceted field of study, and it is an area of active research and exploration. While there is still much that we do not know about the universe and the possibility of life beyond the Earth, the search for extraterrestrial life is helping us to better understand the universe and our place within it. The implications of the laws of the universe. The laws of the universe are the fundamental principles that govern the behavior of the universe and describe how matter and energy interact. These laws have many important implications for our understanding of the world and our place in it. One of the most significant implications of the laws of the universe is the realization that we are just a small part of a vast and complex cosmos. Observations of the universe have shown that it is made up of billions of galaxies, each containing billions of stars. This understanding has helped to put our place in the world into perspective and has opened up new possibilities for exploration and discovery. The laws of the universe also have practical applications in our everyday lives. For example, the laws of thermodynamics are essential for understanding the transfer of heat and work, and they have important implications for the design of engines and other machines. The laws of electromagnetism are the basis for technologies such as electricity and electronics, and the laws of quantum mechanics underlie many modern materials and technologies. In addition to their practical applications, the laws of the universe also have deeper philosophical implications. For example, the laws of cause and effect, which are a fundamental part of physics, suggest that there is a logical order to the universe and that events have a specific cause and effect relationship. This understanding has shaped the way that we view the world and has influenced our beliefs and values. Overall, the laws of the universe have helped us to understand the world around us and have had a profound impact on society and technology. They continue to be an essential part of our scientific understanding of the universe and are an active area of research and exploration. Thank you for reading this book about the laws of the universe. We hope that you have gained a deeper understanding of the fundamental principles that govern the behavior of the universe and how they shape our understanding of the world. The laws of the universe are complex and multifaceted, and they have had a profound impact on many fields of science and technology. From the study of the fundamental building blocks of matter to the exploration of the origins and evolution of the universe, the laws of physics provide a framework for understanding the world around us. The study of the universe is an ongoing process, and there is still much that we do not understand about the nature of the universe and its ultimate fate. However, through the use of experimentation and observation, interdisciplinary collaboration, and the development of new theories and technologies, scientists are working to better understand the mysteries of the universe and to make new discoveries. Thank you again for reading this.